Good afternoon. And in this time is the siesta time in Spanish people. I need wake up, okay? For this, I ask 3 questions. It's very easy question, and I think that another presentation answer this question. But don't worry. The first question is very easy. I need to know how many people know Hadoop. I can say nothing from here. I need show me, okay? No, show me, yes. I need. Do you know Hadoop? Yes. Okay, all right. The second question is more difficult, okay? But I need how many people know Cassandra all the time. Do you know Cassandra? Yes. Okay. And the last one is this is the hardest, Spark. Please, show me one more time. Do you know Spark? Yes. Okay. It's no easy question. If you don't know this name, don't worry. In this presentation, we try to tell you something about this, okay? Okay. In this talk, we present Stratio Deep, an integration between Cassandra, a NoSQL database, and Spark, a distribution framework like Hadoop. With this integration, we have built a new analysis platform on Cassandra. Stratio Deep is a cornerstone in the Stratio Integration platform because all databases need a tool for searching the different information. In this slide, you can see the main components in this platform. Stratio Deep for the analysis search, Stratio Search for the full text analysis, Stratio Real Time for the stream processing, and Stratio Boost. Stratio Boost is a communication framework. It's a glue in the platform. With these tools, we have a complete big data platform. But in this presentation, we are going to focus in Stratio Deep. The goals in this talk are to answer 4 questions. The first one is, we do need Cassandra. This is an important question because maybe you don't know Cassandra, but you maybe need Cassandra because Cassandra is the best option in a lot of cases. Now, you disagree with me, and you know why you need Cassandra and when you must use it. Everything is perfect, but the life is not a bed of roses. Cassandra isn't perfect. I have a little problem, but don't worry. We have a solution for this. For this solution, we need you to Spark. We are going to explain why we have chosen this technology. And finally, on the last one, we are going to show you how Spark and Cassandra work together. Okay, the first one is Cassandra. Cassandra is an incredible NoSQL database. This is based on 2 products, Amazon DynamoDB and Google BigTable. It enhances of Dynamo the replication properties. When you write in the database, this shows up node automatically. It doesn't need to ask because the client knows where the information must go. Also, it enhances the key-value model. This is very important because when you search information, only allowed to search information in the column of the key, because Cassandra uses the key to distribute information. This is very useful because you only need to know the key to be able to allocate information in the cluster. This is awesome because it allows that Cassandra nodes are identical. The distribution isn't master and slave. It's peer-to-peer. Your cluster is fault-tolerant and elastic. Awesome. Finally, Cassandra inherits the column model from BigTable. With this model, you can define metadata information in the table. And this allows that the serialization is implicit in the information, and this is more user-friendly. So you have an hybrid solution between the key-value model and the column model storage. Okay, well, we are going to check the main features of Cassandra. It's robust, but I'm not saying this because it's stable based on Apache, it's open source, it's maintained for the community. No. It's robust because we have tested to write the database version while there was input traffic and nothing happened. That is incredible. It's robust because always is up. It is fast. The write operation are fast. The write operation are fast. The deploy is fast. Fast is a great definition for Cassandra. Efficient. You can do more with less. You can work with Cassandra with few nodes. It's powerful always. It is not only efficient when you have a lot of data. It's is it not only efficient when you have a lot of machines? Is this scale together your application is scaling? More strong points. Cassandra has some bottlenecks because you don't have master knowledge. You don't have completed scaled options. Cassandra is fast because it's simple. Other point, decentralized and replicate. No master, no rules. You don't have a single fault point. And you want to have the information replicating a lot of machines and different data centers. Don't worry. Cassandra is ready for this situation. But maybe you're thinking another database. Why? Why? Maybe you're thinking, why do I need this database? Why do I require this database? Or it's a trap. Nothing is perfect. They have some high-end problem, and they don't want their use. Is Cassandra perfect? No. No. But close enough. Cassandra is designed for a specific and common use case. Our experience in big data project allowed to identify 3 different cases. The first case is the most traditional. When someone explains what is the big data problem, you think in this case, one person searching a lot of data. This case is used when an analyst wants to access in the big data repository. You need distributed information in the cluster because it's too big, but the search process is very, very hard, and the cluster can support many searches concurrently. The main solution for this case is use technologies based on Hadoop, like Cloudera, Mapper, Hortonworks. The second one is a case that many people think that isn't big data problem. You don't have a lot of data, but you have many users search information in your cluster. You need replicate information in this case. And also you need a log system that allows to date the change all nodes in the same time. This case is perfect for other database and no big data technologies, like MongoDB, MySQL, MariaDB. And the last one is a hybrid between the first one and second one. Also, it's the most complete, because you have many users, a lot of data. In this case, you must design the queries correctly, because you need a database that is prepared for a specific search. This is perfect case for Cassandra. This case is common, a lot of samples. Machine-to-machine communication, financial transfers, mobile apps, log monitoring, network sensor, surveillance system. I think that this case is more easy to understand if you have a little sample. Perfect. We have developed a crawler that gets the information of the 2,000 site more relevant in Spanish. This crawler has got a 100 million page of storage. Actually, had more than 3,000 rate operations per second. And we needed low latency hardware for improving our indexed speed. So this case is obviously many users, a lot of data. The third case. So we have chosen Cassandra, obviously. Then when designed the database thinking in the queries. And everything worked, but nothing is perfect. No, nothing is perfect. The marketing people is special people. Our marketing people needed no other information in the data, and they want to search in the data deep. So con la iglesia hemos topado. We received a mail. I need to find all the reference to the domain name. I need the answer by Friday. I don't say thank after the mail, no. That was simple. They needed to search the word name in the reference. Why? I don't know. It was a mystery. But we had a little bit problem. Cassandra isn't designed to resolve this type of queries, because you must think the query before you design the database. But we are big data experts, and we can resolve big data problems. So we find the solution for this problem. Get a file. Look and explain you how we did it.
So as Alvaro said, can you hear me? So as Alvaro said, we've got a problem because we need to solve a query, and our database schema has not been designed to solve that query. So we tried to find some solution. We looked around, and in the end, we came to to three options. We had three options in order to solve this problem. So the first option is to run Hive queries on top of Cassandra. There is a native integration using the Cassandra storage handler. And we found that this solution is not feasible because what it really does is moving data from Cassandra to HDFS and then executing the query over the data in HDFS. So it's not feasible because basically we need to move a huge amount of data. So second option is to write an ETL script and load the data into another database. We've got the same problem as before. We have, well, here, really, we have got two problems. We need to choose another database which scales and which is good at performing queries, and we have to develop and maintain an ad hoc ETL script. So this option has been discarded. And so the third option is to clone the cluster, or maybe clone the Cassandra table, and create another schema that is able to solve our query. So none of these options are feasible because basically all of the three options requires moving a huge amount of data. So what did we do? We did basically a lot of research, and in the end we came at Spark. So what is Spark? Spark is an implementation of a research paper called the Resilient Distributed Dataset, also called RDD. So this research paper has been developed in Berkeley, and the implementation itself has been developed in Berkeley. So what Spark does is basically changing the way that we see big data queries. I mean, Google MapReduce has been optimized to solve one-pass batch processing on disk data, while Spark has been designed to solve more complex multi-pass analytics algorithms that are becoming really common. So it scales very well, and it has low latency, because it basically caches all the information that the most information in memory, and here we got a benchmark done by Berkeley, where we can see how well Spark scales on an algorithm performing many iterations. This comparison has been run against Hadoop. So these are a few companies that are actually using Spark, because Spark is stable. It is a young project, but it is really stable. So we need to integrate Spark and Cassandra. So we had to find the possible integration points between the two frameworks, and we had basically three options. The first option is develop an HDFS abstraction layer on top of Cassandra, which basically translates all the calls to HDFS to Cassandra. This solution is a clear winner when you have to integrate Cassandra with legacy systems developed using Hadoop. But it has a lot of drawbacks. The most important drawbacks is that there is a huge impedance mismatch between what a NoSQL data store like Cassandra is and a distributed file system like HDFS is. And so the integration is somewhat tricky, and we had to discard it because we didn't like it. So second option was the Cassandra's Hadoop interface. Cassandra comes with a built-in interface to Hadoop. There are two implementations. The first one based on Thrift, which is the older one, and the newer one, which I think has been introduced in Cassandra 1.2, based on CQL3, which shows the Cassandra Hadoop's interface based on CQL3. So this implementation uses the new object CQL paging input format included in Cassandra 1.2. So we chose this way. We chose this path. And what can we provide with this integration? Well, basically, what we do is to support all of the CQL3 features, like, for example, composite keys and so on. And more important, what we do is to respect data locality. What does it mean? What we do is to map Cassandra splits, which basically are data partitions, to Spark's partitions. and this let us perform computation and to ensure that when possible, data is fetched from the local machine and is not being transferred on the network. And moreover, our implementation did not require developing a lot of code, so it is quite compact, it is simple, and it is elegant. We are really focused on Java, and we really focus on providing a very Java user-friendly API. Why? Spark has been developed in Scala, and it is not always easy to develop a Java application using Scala libraries. So, moreover, one of the novel things, one of the unique features of Stratio Deep is that we are providing a completely generic interface to developers, and what we do is provide to developers a way to specify their own POJOs, and later all the computation in Spark will be done using this POJO, and under the hood, Stratio Deep performs the mapping from the Cassandra columns and the POJO properties. So let's see Stratio Deep at work. But before diving into Stratio Deep and doing this demo, it is important that everybody understands a few basic concepts of Spark. The first one is that Spark comes with a command line shell that lets you quickly test and prototype your code. Okay, so Spark has been developed in Scala, as I've already said, and the Spark shell has been built on top of the Scala shell. In this demo, all of our code will be done in Scala. But for those of you which are not familiar with Scala, well, don't worry, because the examples are really simple, are really straightforward. And second, the main abstraction, as I've already said, the main abstraction in Spark is what we call the RDD, the Resilient Distributed Dataset. So in order to construct an RDD, we first need another object which is the main entry point to Spark, which is the Spark context. So we are going to see how to use a Spark context. In this demo, I want to underline that in this demo, everything is running on my local machine. So there's no connection at all with the cloud or nothing else. So don't expect things to be as quick as they would be on a real cluster. So we are working on a little data set of 20,000 web pages crawled from the internet. So let's see how this data set is the structure of this data set, and later let's go dive into Stratio Deep. Okay. So here we got the log of the Cassandra cluster, and here on the left we got the log of the Cassandra cluster, and here we already got I've already opened a CQL shell. CQL is the native Cassandra query language, and we will see how Stratio Deep will let you perform operations that are not possible using CQL. So in this data set, we've got a table called page, okay? And a page has a lot of properties, but in this demo, we are going to use only a domain, the domain name, and the response code of the web page, okay? So let's see how many rows we've got in this table page. We got a little bit more than 20,000 web pages. Okay, and so let's start Stratio Deep. Okay. The Stratio Deep shell is based on the Spark shell. And here, what we do when starting Stratio Deep shell is importing some basic packages and classes that we need in order to do our computations. Okay, so we got the Stratio Deep shell start, and when we first start a Spark shell, what Spark does is providing you a pre-construct context. I want to remember that the Spark context is the main entry point to all these Spark features. So the already provided Spark context is called SC, is the default Spark context. As you can see here, Scala is showing you the type of the object. So we must construct our own context, the deep Spark context. And we construct this Spark context based on the default context provided by Spark. So deep context is a new deep Spark context based on the default one. Okay. So we've got our object. As you can see, Scala is showing you the type. Scala type inference calculated the type of the deep context, and that's it. So now, once we've got the context, we can build the RDD. But before building our RDD, we need a configuration object. I mean, our RDD needs to fetch data from Cassandra. So we need to pass to this RDD the connection string, the key space, and the table name. Okay. So in order to do that, we got an ND factory that will help you to construct the configuration object. Okay. So the config factory create. Okay, here when we create the configuration object, we need to pass something more than the connection string to Cassandra. If you remember, a few minutes ago I said you that our implementation of an RDD is completely generic, and you must provide your own POJO. Okay, so we provide our POJO to the configuration object. Okay, so let's see, for example, an example of a POJO, of a POJO mapping the Cassandra table structure to an object. Okay, so here we've already provided a POJO that has already been imported in our context. So you can see that it's basically this is a simple class. This interface is just a marker interface which extends serializable, and we've got a few properties here annotated with a special Stratio Deep annotation. So let's get back to our code. So let's get to our code and let's create the configuration object. We pass the class of the page entity, which is our POJO, okay? And we also pass the key space. And we pass the key space name, which is crawler key space. Okay. And we also pass the name of the table. In Cassandra terminology, column family, a table is also called column family. And here we use this notation. The table, if you remember, is called page. Okay. So now we can initialize our object. This is a fluent interface, and we can assign the result to a variable object, to an object called config. Okay, so now we've got our configuration object. Let's wait for a second to initialize this object. This operation is you need to do this operation just once when you first create the configuration object. So here again, Scala type inference calculated the type of the configuration object. So once we got the configuration object, we can finally build our RDD, a Cassandra RDD, which is the main abstraction in our integration. So for example, let's create an RDD, and we have to use the context, and in the context provides a few factory methods that will make life a little bit easier for you to construct an RDD. So here we are using Scala, so we are using the factory method of Cassandra RDD, but if you develop in Java, I really suggest you to use the Cassandra Java RDD. So, okay? And to this factory method, we need to pass the configuration object. And that's it. We've got an RDD, okay? Here, the Scala type inference says that we've got an object of type Cassandra RDD of page entities, okay? So let's start doing some computation. Well, the first computation that I want to do is just to compute the number of rows in our table, just to compare it with the query that we've done in CQL a little while ago. So let's do, for example, an rdd.count. Okay. So here, what we are doing, what Spark is doing, is to distribute the calculation. In this case, our cluster is composed by just one machine. In the case that we had a cluster of many machines, this will be distributed among all the cluster machines. And here you can see that the query is really run against the Cassandra cluster, as you may have seen in the Cassandra logs. Okay, so we've got a little bit more than 20,000, 21,995, which matches the result of the query that we've done earlier. Okay.
Okay.
So now we can, for example, do something. Now we can really see something that the power of Stratio Deep, and I'm going to show you something that you cannot do with CQL. Okay. So for example, let's calculate an RDD of all those pages whose domain name contain abc.s. Okay, so this is something that is not absolutely possible with CQL. So you can, for example, in CQL using secondary indexes, match all those pages whose domain is abc.s, but you cannot find all the pages whose name contains abc.s. So abc RDD, for example, we calculate this as an RDD dot filter. And here, what we do is pass a filtering function. A filtering function is a function that maps from the domain to a Boolean. So what's our domain? If you remember, our RDD is an RDD of page entities. So the filtering function is a function that accepts as an element a page entity and maps it to a Boolean. So here we want all those pages whose domain contains abc.s. So we do this. Contains abc.s. Okay, that's it. So we've got our new RDD. You can see that here we've got another RDD whose type is the same as the other one. It's an RDD of page entities. So now let's, for example, see how we can cache this RDD. Okay, so cached is abc RDD.cache, and this is a function provided by Spark. So and now let's see, for example, well, the number of elements of this new RDD. Okay, so let's count it. As you can see, this count operation is taking a long time. Well, it's not taking a long time. It's taking a little bit of time. Why? And all the other operations that we've done previously to calculate the other RDDs were instantaneous. Why that's it? Because in Spark, we've got two types of operations. We've got transformations and we've got actions. Transformations are calculated lazily, while actions are the operations that really trigger the calculation on the underlying data set. So here we've got a little bit more than 300 pages. So let's filter a little bit more this RDD. Okay. Well, I want to show you that now, if I perform once more the count operation once more, the result is instantaneous because the RDD has been cached. Okay, so let's filter a little bit more these RDD. Let's get, for example, all those pages in this RDD whose response code is 200. I mean, all those pages that have been downloaded successfully. So, for example, we can create a new RDD called abc-ok, which is calculated on cache, and we filter. we filter again. Here, filter is we must pass a filtering function. The data type of cached is an RDD of page entity, so we must provide a function that maps from page entity to a Boolean. We are interested in all those pages whose response code is 200. So okay, so get response code. This returns a Boolean, and that's it. We've got the filtered object. So now we can, for example, we can count the number of elements in this RDD, and we can collect the elements. So for example, the collect operation is an operation that what it does is to return you the raw data, the raw data contained in the RDD. Okay, so here basically Spark, what it does is to return us an array. Okay, an array of page entities whose size is quite big, because they are a little bit more than 3,000 entities. So now let's see something a little bit more involved, a little bit more complicated. We want to perform a group by over this data, and that's something that it's absolutely impossible in CQL. Okay, so let's do this example, and let's use a Spark function called group by key, which is quite handy, it's quite useful. But what it needs, the group by key function works on an RDD of key value pairs. So now here we have an RDD of page entities. So we must map this RDD to another RDD of key value pairs. We are interested in grouping our RDD by domain, okay? So we construct another RDD of key value pairs where our key is the domain and the value is the entity itself. So let's see, for example, grouped not, it's by domain. It's our ABC, okay? Okay, and we must map this RDD to another RDD. So to the map function, we must provide a mapping function. And the mapping function, what it does is accepting an object of the domain of the source RDD, and we need to return an object in the domain of the result RDD. So we accept a page entity object, and we return an object which is a pair of key values. Okay, in Scala, a pair is constructed using is called a tuple. In this case, is a tuple of two elements, the key and the value. So the key here is the domain, and the value is the entity itself. Okay. So let's calculate this new RDD. As you can see now, Scala type inference says that we've got an RDD of pairs of a string and a page entity. Okay, the string represents our domain. Okay, so now we can really perform the grouping. Okay, so we just by domain, we just do this calculation by domain dot group by key. Okay, and we assign this result to a group. Okay. Again, this operation is lazy. We've constructed in memory the object, but we've not really calculated the content of this new RDD. So now with this group, you can see here, it's very interesting, because now the type of the resulting RDD is a pair where the key is the domain, and the value is a sequence of page entities. We've grouped all these page entities by domain. So now we could collect, for example, we could collect the elements in this object, but remember that the sequence of page entity may be a sequence of maybe thousands of elements. So let's do something more. Let's, for example, count the number of elements in this sequence. So what we need to do is to map this group the RDD to another RDD whose type is a key value RDD, where the key is the domain and the value is the size of this sequence here. Okay, so let's do that. It's val filtered or well mapped, and it is grouped map, and the mapping function accept a tuple, which is the tuple that we've seen here earlier, and the first element is the same element, and the second element is the size of this sequence. Okay, this is the mapping function. Okay, so here now we got an RDD of domain of pair of string integers, and we can, for example, collect the element and see the result. So here we've got our result for each domain. We've got the count of the elements in this domain. So there's a lot of power here. We could go on doing many more examples. For example, doing joins between tables in Cassandra, but this goes beyond the scope of this demo. So let's go back to our slides, and let's see what are the shortcomings of our integration, where we're still not performing as well as we would like. And that's basically because of we think that's because of the Cassandra Hadoop interface. And moreover, the most important thing is that we still do not provide an interface friendly, SQL-like user interface that any data analyst could use. So we are currently working on these two things. We are exploring another implementation of the integration where what we do is dump the Cassandra Hadoop interface and experimenting, accessing directly with Cassandra SS tables. And the second one, we are extending the COL3 language, and we want to provide additional constructs in order to perform query using a SQL-like language, but that trigger computation using Spark. So here is the result of our architecture. What we do is another case. What we realize, what we achieved is another case in which we got many users, a lot of data, and we also give the possibility to data analysts to use this data, to exploit this data in order to provide a value for the business. And that's it. Thank you very much. Any question?
Hi, my name is Surinia, and well, I work for a company whose name is Praxis, and we also work with Hadoop, and we tried a bit about Spark. I understand that you use Spark because you want to improve the shortcomings that you have with Cassandra. As for the SQL possibilities, such as having joins and things like that, or secondary.
Yes.
Secondary sort. Haven't you tried using Shark? I mean, this is a product on top of Spark, having a SQL interface.
We talked about Shark, and while designing our architecture, we finally decided that there was no room for Shark. So what we did was to decide that we're not going to use Shark, and we were using the way that I just explained. So well, basically,
really the problem with Spark is in the architecture. I don't really on top of Spark. When you design the SAR in the main string of the SAR design, is a group different in the Spark and the Spark. Now is when you refactor the SAR and convert SAR top of Spark. When you analyze the problem the SAR, we need to integrate the Cassandra with two tools, with SAR and Spark. I think that it's more easy to integrate with the Spark and create a new layer in SQL for a Spark integration with Cassandra.
Basically, we were not interested in the the Hive, in what Shark is providing us. So we are not interested in the Hive query language. So we are really not going to use that in our architecture. That's basically that's why we didn't choose to integrate Shark.
Okay, thank you very much.
You're welcome.
Hello, thanks for your talk. I would like to know if you have tested Spark for streaming and if you can say anything about it, if you compare it with Storm or another streaming technologies like S4. Thank you.
We really didn't. We really didn't, and that's something that we got in our pipeline, and we really need to test it.
Yeah, Stratio real-time product is over.
we are thinking about in our architecture. The architecture has not been fully developed, and in our architecture there is a real-time layer, and we are not. We are talking about how to implement the tools that we are going to use in order to implement this layer. So if there is no more question, I would just like to say one more thing. That if you're interested in trying Stratio Deep, you can download it. You can download our platform from the stratio.com. You can test it. You can test it using the very same dataset that we used here in this talk. And please provide us your feedback. So if you got any more questions, there is any more.
Okay. Thank you very much, Alvaro and Luca.